Let's do this. Okay, so we didn't quite get through the memory diagram last time, so let's pick this up here. And judged by the timing of the last lecture, we should be able to get through all of today's content as well. So let's jump into it. So we left off roughly about here, but let's get our heads back into this memory diagram. So we're sorting using a comparator. We're sorting the values of an array list using a comparator. We're creating a new output list. We have a reference to an input list. We're going to be very careful with our reference. We don't want to modify the input when somebody's not expecting that. If they call sort, there's kind of two approaches. You could either sort the list that they give you or return a sorted list. We're returning a sorted list, so we don't want to modify the one that they gave us. So we're creating a new array list. And I'm saying list. If I say list today, in the context of today, I mean array list. Array list is just so many syllables and I forget to say them. So we're creating a brand new output list. And we're entering this outer loop. So when we enter a loop, we're doing our dashed box to indicate that we're in a code block. Inside this code block, we have the iteration the iteration variable value to insert, and initializing location to 0. And then for this iteration of the loop, value to insert, getting the value 1 because that's the first value in this array list. We're iterating over these values, so this will be 1, 6, then 5 as we're going through. And we're going to get to the second loop. This loop is looping over all of the values of the output array list, which is empty. Since it's empty, we completely skip over that inner loop on this iteration. We don't do anything. Body of loop doesn't execute at all. So nothing to do. We don't draw our code block or anything because it never executed. Not a single line of that loop executed, which does happen. Something we always have to keep in mind when we write a loop. It might not execute at all. So if there's some logic, some code in here that you need to run at least once, and you have it in a for loop, it might not run at all. Then we're going to add the output. We're going to add at location 0, adding this value to insert 1. So at index 0, we're going to add the value 1. So that was the first element in the input list. We know we're just going to add that to an empty list. Not much going on with that one. And our code did the right thing, added it at index 0, added that value. For the next iteration, we're going to update value to insert to 6, moving on to the next element of this list. Remember, we're iterating over all the values in input, and we're storing each value in value to insert each time. So this, eventually the 6 will get crossed out, and we'll have a 5, and then that will be the last iteration of the loop. And then int location equals 0. We're treating this as a reinitialization of location. And even when we do an assignment operator to the same value, we still do cross out that value to show that a line of code did actually replace this, just happened to replace it with the same value. In this case, we have a little bit more going on. If you want to get technical about it, this is the way we're going to do it. Just cross out the value and write the new value. But whenever we see a type and then the variable, that is a variable declaration. We are creating a brand new variable. So when we say int location, that creates a brand new variable. We're treating this in our memory diagrams as a special case, even though a new variable called location is being created. In our memory diagrams, we're just going to cross out the old value and write in the new value. So it is a new variable, but actually in memory on the stack, that location variable is removed from memory. A new location variable is created in the same exact spot in memory and then initialized to 0. So it will actually reuse the memory, so I'm comfortable with this shortcut of instead of like crossing out this variable and then writing location again and then 0, let's not do that. We'll just cross out the value, even though it's being redeclared. So just a little caveat, a little special case. And now when we get to the inner loop, it actually does execute this time. We're going to iterate over the values of the output list, which is just 1. And we do have a loop inside of a loop. This is perfectly normal, acceptable, something we can do and that we do all the time. Though I think it's the first time it's come up in this semester. I think it's the first memory diagram I've shown with nested code blocks like this. But we just draw a dashed box inside of a dashed box. Then this dashed box is inside of a stack frame. Oh, that's perfectly allowed. And all these variables are still in scope. They're all still in the same stack frame. We can see them all. So dashed boxes, and we can cross those dashed lines to access the variables that we are using. And then we're going to get to our first comparator call. This dot comparator dot compare. So from this object we're calling compare. It's of type int decreasing. We find a compare method, and this is the method we're going to call. So we call compare. This is 350, the calling object, which actually isn't relevant in this case because we're not accessing any of its instance variables. It doesn't even have any instance variables, but it is what this is. And then AB16, value to compare, value to insert, 16, and it's going to return false. So it's going to do this comparison. Oh, yeah. Stack frames, I did the whole build-up and didn't mention the payoff. Our code blocks do get nested. Code blocks inside stack frames all day. We can do that. But stack frames never, ever go inside other stack frames. Hopefully you're all beyond this one. We've been doing this for a while. Once you get through classes 1, this is where we see the mistake on the classes 1 quiz. So then we can straighten you out on that and avoid that. Stack frames never go inside other stack frames. They are actually separate spaces on the stack. They are completely separated in memory. They're completely different things, different entities on the stack. So in our memory diagrams, we draw them as separate entities. This stack frame is completely isolated from this stack frame. Inside this stack frame, we can't access any of these variables. Inside this code block, we can access the other variables. So it might sound like just a notational difference. We draw these things different than these things. There is an actual reason for that, a big reason. Inside this code block, we can still access these variables. Inside this stack frame, we can't access any of these variables. The sorter, we can't access any of those. It's its own environment. So we draw it separate outside of everything else. It doesn't make sense for a stack frame to be inside a stack frame in the computer, the way the computer is actually running. So we don't draw it like that in our memory diagrams. So this stack frame is going to compare 1 greater than 6 is false, returns false. Since it returned false, we're not going to update location. We skip the conditional code block. Location is still 0. We've reached the end of this loop. That loop is removed from memory. Value to compare is no longer in memory. And we're going to add at index 0 the value 6. So 6 gets added at index 0, and then everything else in the array list, which is just the value 1, gets pushed down the array list down to a later index. So 1 got inserted at 0. 6 also got inserted at 0, so 1 got moved down to index 1. And this is how we're maintaining that sorted order in this output array list. Create a new location. We're going to just cross out the value and rewrite 0 again. Not super interesting when we're crossing out 0 and writing 0, but still, that's something we'll have to do. And then moving on to the next value in the input array list. That's what this loop is doing, updating value to insert up to 5. Hit the inner loop. We're going to create another code block for the second time we're hitting this loop. Third time we're hitting it, I guess. Second time we're executing this loop. For this, we will write separate code blocks for each time this loop executes. Value to compare is going to iterate over the values in this output list, 6 and 1. We're going to call our comparator again, comparing 6 and 5. And this time, the comparator is going to return true. So we're going to increment location to 1. Call the comparator again with 1 and 5, returns false, so we don't increment location. And we found the location to insert 5. We're going to insert it at index 1. So we insert 5 at index 1. The value 1 gets pushed down to index 2. The outer code block ends, the outer loop ends. The method ends. We return a reference to this output array list. We can print it to the screen, and we see that we do get our ints sorted in reverse order, in decreasing order. So this works for our input of size 3 because, it fits on a slide with the whole memory diagram. But if we want to sort 1,000,000 values with this algorithm is going to work. It's going to go through and find for each value in the input list, where does it go in the output list, insert it at that index, move everything else down, and just keep doing that until all 1,000,000 elements are fully sorted in the output list. All right, so any questions on this, on Friday's content? No. Last message is from me, so no questions. Move on to today's content. Oh, that's still going to be wrong, isn't it? Okay, binary trees and traversals. So let's talk about our next data structure, the binary tree. So binary trees are similar to linked lists. With linked lists, we had a node-based data structure that had the value at that node and a reference to the next node in the list. And the next node had a reference to the next node had a reference to its next node, and we linked these nodes together until next was null. That's how we knew we were at the end of the list. Binary trees are going to work very similar. They are also a node-based data structure that are going to store the value at that node, except instead of just having one reference to the next node, it's going to have two references to two other nodes, called the left node and right node, or the left child and the right child. So two references instead of one, and that's it. That's the difference between trees and linked lists. Otherwise, everything you know about linked lists, the structure of a linked list applies, except the algorithms that we write are going to have to be a bit different because we have to work with two nodes instead of one. So a little bit of vocab. These nodes are called the child nodes of that node. We have a left child and a right child. And to those children, that node is the parent node. I won't belabor it, but there's the whole family tree analogy. All that vocab applies to these trees. For 116, pretty much just child node. I say pretty much, but we're going to use child node. Every once in a while, I might say parent node, but it's less relevant just for the things that we're going to do in CSE 116. But understanding that the left and right references are references to something we refer to as child nodes. Just a bit of vocab we will use extensively throughout this week. Visually, it's going to look something like this. Each node has a value, and then a left and or right child, which will be references to other nodes, and those references can be null. For a bit of the examples, I'm going to use this tree because it's nice and symmetrical. It looks good on a slide and everything. But don't fall into this trap. You can have trees that are not balanced like that. So if left refers to a node, don't assume that right refers to a node. If left refers to null, don't assume that right refers to null. You can have these imbalanced trees. And we will see an imbalanced tree when we get to the memory diagram. I've seen a lot of students make that assumption that in their code they'll say if left equals null, then don't even look at the right node because it's obviously null. Don't make that mistake in your code. I used to always show just this in the slides. That's when I saw that mistake a lot. So I make sure I mention that to make that clear. And here it is in code. So our binary tree node looks just like the linked list node, except we have two references to other binary tree nodes. And also has its value. We have our generic type A, a constructor, which just sets the instance variables equal to the values, the parameters of the constructor. It gets a bit different when we start actually working with the tree. So the structure of the tree, pretty much the same. When we work with the tree, we see a bit of difference here. With linked list, we had a prepend and an append method. We didn't really write the prepend method explicitly, but in our main methods, we would prepend to the linked list to be able to get those values replacing the head of the linked list. With binary trees, we're not going to see a really clean way to just add elements. Actually, Wednesday we will for BSTs specifically, binary search trees. For regular trees like this, we're just going to build them manually. It's the easiest thing to do. So we're going to set the root node, just like linked list only has a reference to the first node in the linked list. Same with trees, except we call that node the root node instead of the head node like we did in linked list. The root of the tree, because of course not just the family tree analogy, but the actual biological tree analogy with roots. Everything starts at the roots, and then it gets, there's a lot. It gets branches and leaves, and we're not going to belabor all the analogies, though, in 116. Other classes will, and they should, because they got to talk about a lot more than we're going to talk about. So create the root node, and that's going to be a reference to a new binary tree node with a value and left and right children being null. And then we're going to manually set the right and left child nodes. We're going to set root.left equal to a new node, root.right equal to a new node, so we've replaced these nulls, then left.left, left.right, etc., to build that tree that we saw visually on the previous slide. So this code is going to build this tree. Now, I kind of have it separated in the slide, but this code is in the same class as the binary tree node. So this is why we're allowed to set the private instance variables directly. So if you're wondering how we're getting away with that, it's because this code is in the same class. Private variables can only be accessed inside the same class, but this code is inside the same class, so it's perfectly fine. Otherwise, and the reason we're doing that is just for logistics. It just gets messy with getters and setters. Like this line would be root.getRight.setLeft, and then the constructor, which isn't too bad on this slide, but when we get to the memory diagram, when that's 2 extra stack frames, it gets cluttered. So that's the structure of a tree. Any questions on this? Let me take a breather right here. Any questions on this before we get into algorithms? Because this is everything I want to talk about the structure of a tree. The rest is just implications of this. Yeah. Mm-hmm. Oh, yeah. So the question, why do I have an A here for the generic type when for linked list it was a T? So that is a variable name. You can use any name you want for that. And for this code, I don't know. Paul decided to use A instead of T. A is pretty common. Just, I don't know, people choose the first letter, I guess. T was for type, just short for type. But they are just variable names. We could put the underscore type or something like that in place of A, and it would still be okay. But for whatever reason, for generic types, the standard is a single uppercase letter. Which letter you choose is whatever. Yeah. Mm-hmm. So we're going to this root node, and we're going to its right child, which was replaced right here. So we're saying root.right. So root.right, whatever this value is, we're going to set it equal to this new node. And then when we're saying root.right.left, we're saying root.right, which will be this node, .left, replace this null with the new node that we're creating. Okay, so what do we do now? We have nodes, they have references to 2 other nodes. How do we work with these things? With linked lists, this wasn't too hard. So, by the way, the first thing we want to do, we're going to build effectively a 2-string method. But in general, we just want code that's going to visit every single node in the tree. And we have to be careful when we do this because we want to make sure we hit every single node, visit every single node, and don't visit any node twice. So it seems like we got a bit of bookkeeping to take care of. With linked lists, this was easy. You just made a recursive call on the next node, and if you ever make a recursive call on node, or you can check beforehand if next is null, then you're done. And you've visited every single node. You just go down the list. But with trees, when you have branching paths, it gets a little trickier, on paper at least. So our solution to this, well, if we're using recursion, and this is where we're going to really see the recursion pay off. We're using recursion, instead of just making one recursive call, we make two recursive calls, and that's it. Recursion does all the rest of the work. Done. Problem solved. If you were using loops with linked lists, this is where it'll start catching up to you, specifically task 6. This week's of content is for task 6. Task 6 is where it'll catch up to you when, if you don't have practice with recursion, that's where you're really going to want recursion. It's going to do a lot of work for you. So specifically, we want to see 3 different algorithms: pre-order, in-order, post-order, traversals. These are all the same concept, our tree traversals. All 3 of them are going to visit all the nodes in a tree, but they're going to visit them in a little bit different order. But they're all going to look very similar code-wise. If you understand one of these, you understand all 3 of them. So let's understand all 3 of them. So in-order traversal, and again, this is effectively a 2-string method. We're going to concatenate all of the values as strings in the entire tree into one string, and then it could be printed to the screen. We can print to the screen here. So we're going to traverse starting at the root, and then if the node is null that we're currently visiting, just return the empty string. If the node's not null, we're going to make a recursive call on the left child, concatenate whatever that returns. It's going to return some string. Concatenate that, which should be a string representing everything to the left, everything in that left, what we call subtree. It should contain all of that as a string. Then we're going to concatenate the value at this node to the string that we're going to return. And then do the same thing with the right recursive call. Recursively call this on the right. Whatever it returns, concatenate that to this out variable, and then return out. So we're going to make a recursive call to the left, visit this node, and then make a recursive call to the right. For pre-order, we do the same thing. We just order our recursive calls a little, well, actually, the recursive calls aren't ordered differently. We order our 3 lines of action here, a little bit different order. We're going to visit this node first, and then make our 2 recursive calls. Post order, you guessed it, we're going to make the recursive calls and then visit this node. The only difference between these 3 traversals is when you visit the node, either before the recursive calls, after the recursive calls, or right in between the 2 recursive calls. All 3 of them, in order, make the visit the node in between the 2 recursive calls. Pre-order, visit the node before the 2 recursive calls. Post-order, visit the node after the 2 recursive calls. Those are the differences. Other than that, it's the same idea, same concept, same stuff going on. Make the 2 recursive calls and visit the node. And with recursion, just a couple lines of code. Like, there's not a lot of extra code. We're doing something much more complex, navigating a tree instead of a linked list, but the code isn't much more complex. The code's about the same if you're using recursion. So my challenge to you, for any of you who want to take me up on this one, write these without recursion. Pick at least one of these and write it without recursion. If you are not sold on the power of recursion, the benefits recursion has for us, just try writing one of these without recursion. It's significantly harder. It's much more work, significantly more work than what you see on screen here. It can be done for those of you who, if there's anyone who does want to take me up on this, a few recommendations. So what we'll see in the memory diagram is that the program stack is doing a lot of work for us. Stack memory and just the order of the stack frames That's what's doing all the work here. Our code isn't doing much work, but the stack is. And the key thing is that each stack frame, when it makes a recursive call and then gets the return value from that recursive call, it's going to remember where it was in this execution. So each node is going to be visited 3 times. We'll pick on in-order traversal here. First time you visit a node, it's going to make the left recursive call. The second time you visit a node, or the second time that stack frame gets control again, it's going to know where it was and pick up execution right here and run these 2 lines of code, visit this node, and then make the right recursive call. And the third time this stack frame gets control, it's going to return the out value. The stack keeps track of all that for us with recursion. If you're not using recursion, what you want is a stack. Like, you'll have to build your own stack, the data structure, and keep track of the order in which you're visiting the nodes. How many nodes are currently, how many, with recursion, how many stack frames are on the stack and in which order. And you'll have to keep track of what visit it is whenever you reach, whenever a node is at the top of the stack. Is this the first, second, or third time I've seen this node? Because that's going to determine what you're going to do when you get to that node. Either add another node to the stack, which node to add to the stack, left child or right child, or visit this node, or return. All that's going to be decided by how many times you visited that node. So something to keep track of all that. It's going to be significantly more code than these traversals. So if you're not a fan of recursion, try it. My guess is, unless you're just strictly looking for a challenge, my guess is if you're not a believer in recursion, you're going to give up on the non-recursive methods here and just suck it up and learn recursion. Or just type random stuff until it works, which is unfortunately more likely. So any questions on this? Actually, let me just do the next slides because these might answer some questions. So with our traversals, I'm going to very quickly go through each of the 3 traversals on this tree, and then we'll slow it down and go through a memory diagram with a different example and go through the whole thing, look at all the stack frames and everything. But just very quickly on these ones, if we're doing an in-order traversal on this tree, we're going to call in-order traversal on the root. The root's going to make a recursive call to the left node. That node is going to make a recursive call to the left node. That node is going to make a recursive call to the left node. This node is null, so it's not going to do anything. It just returns empty string. And then we visit this node. We're going to concatenate -3.toString. We're going to add that to our result. Then make the recursive call to the right. And then this node can finally return. We visit 2. So we got -3 first, then 2. 2 concatenates itself. We visit this node, go to 4. Left recursive call, visit, right recursive call, return, return, return. Visit 5. 5 gets to make its right recursive call, left recursive call, left recursive call, visit 7, recursive call, return, visit 8, then visit 14, and return the final answer. So visit the nodes in that specific order if we're doing an in-order traversal. So in short, like if you look at the root node, we're going to visit all of the values to the left. We visit all those values, then we visit the root, then we visit all values to the right. And that's true for each node. For 2, we visit -3 to the right, then the node, then 4 to the, -3 to the left, the node, and then 4 to the right. And then return back to 5, visit 5. For a pre-order, we're going to visit the node, then make recursive calls. So the root is going to be the very first node visited. Then we visit 2, then -3, then make our recursive call of null, null, visit 4, recursive calls, visit 8, visit 7, these return, visit 14, and then everything returns back up. With post order, just the opposite. We're going to make the recursive call, recursive call, recursive call, recursive call, then finally visit a node. -3, recursive call, visit 4, visit 2, visit the right, recursive calls, visit 7, visit 14, then 8, and then 5. The root will always be the last node visited in a post-order traversal. So we can see everything to the left of the root everything to the right of the root, and then the root itself. And for each subtree, visit everything to the left, then everything to the right, and then the node itself. So conceptually, the same thing with all three traversals, but we get different orderings each time, depending on which traversal we use. Different order of visiting the nodes. All right, questions on this up to this point? Next thing's a memory diagram. That's the structure of a binary tree, how traversals work. The next thing is making it all super explicit with a memory diagram. Yes? For a post-order traversal, yes. So because it's going to make these both recursive calls before it visits the node itself. So in this case, it'll go, like on this node, it'll make the recursive call to 3. 3 is going to make 2 recursive calls, both of null, so they don't do anything. And then visit 3, -3. Return to 2. 2 is going to make its right recursive call. This node will make its left recursive call, right recursive call, then visit 4. Will be the next value. And then 4 is going to return, get back to this node, which just got its return value from its right node, its right child recursive call. So then it's going to visit 2 and concatenate 2 to the overall string. Does that make sense? Sound good? And like for the root node 5, it's going to make its left recursive call. That recursive call has to do all of its stuff before it returns to 5. Then it's going to make its right recursive call, which is going to do all of the stuff over here before it returns. And then we finally get to concatenate 5 to the very end of everything. And then return back to whoever called the method to begin with. Right. Any other questions before we get into a memory diagram? I'll let you stare at this code for a little bit too. I'm going to switch up to a tree of strings. There's going to be one mistake. I just updated the slides, but it's going to have a different mistake now. This shouldn't say root dot. It should just be traversal of root. Very quite minor thing. But it is incorrect. All right. So let's go through this. And I'm omitting most of the code for the binary tree node, and I'm abbreviating BT node, usual memory diagram stuff, so things fit on the slide. I'm going to omit the code, just a reminder if you forgot what the code is. The constructor just takes the 3 parameters and stores them in instance variables of the same name. So that's the code I'm omitting here. Okay, let's do it. So we have a lot of object creation to create our tree. First, we're going to create a variable named root, which is going to be assigned a new binary tree node. So we're going to call the constructor, create a new object on the heap. The constructor parameters are going to be assigned to the instance variables in this case. And we have a binary tree node of with the value day and left and right being null and null. That we've seen 100 times by now. We've seen a whole bunch of objects being created on the heap. The next one, a little bit different. This is something new we haven't quite seen before. So root.left equals, and then a new binary tree node. So with this, this is the first time we've seen this where we're assigning an instance variable directly. I can get away with this even though the values are private, again, because this code is all in the same class. If not, I'd have to do root.setLeft, and we'd have extra stack frames, and I wouldn't be able to fit it on the slide. So root.left equals, so we're replacing this value, whatever the right-hand side evaluates to, that's the value we're replacing. So when we create our stack frame, we do have to have our return arrows, and the return arrow is going to point to the variable that's being replaced, the variable whose value is being replaced. So root.left is what's being replaced. We are actually going to draw an arrow over to an instance variable on the heap. So we will draw our arrows to whatever variable is being replaced. Create our node with the value have, update it, and then same thing for root.right. We're replacing that null from the constructor call. We're replacing these two nulls. We're replacing them with these new binary tree nodes. And then root.right.left, root. And again, with these memory diagrams, it feels weird to recommend, but I recommend turning off your brain a little bit and going through these character by character. The machine, your computer, can go through this, can read this code and go through it line by line. And your computer has an IQ of 0. It doesn't think at all. So sometimes thinking actually does get you in trouble in these things if you're trying to look ahead and plan things out and things. Sometimes you want to do that for like space reasons. You want to plan out how big your stack frames should be drawn. But root.left.right, you just look at what's on your stack, what's in memory. Root, dot, right, dot, left. So we're replacing this value right here, equal to a new binary tree node with the value A. So we get that new reference, replacing that null, root.right.left. And our tree is fully created. And I expect on the tree quiz, if you want to draw out the tree, it definitely helps you. We won't grade whatever visuals you draw, but if you draw out the tree, it definitely helps you as you're going through the memory diagram. Instead of going through the heap and seeing, okay, root is here, left is this, right is this, the right's left is this. It's a little harder to see in memory itself, so drawing the visual always helps. Let's do this. We're making a recursive call, then visiting each node. So we're looking at a post-order traversal here. And I cleaned it up a little bit from what we saw in the traversals before, the other code. I'm just going to print to the screen directly here instead of concatenating them all into one big string and then printing when we get the return value. Again, it's a lot less messy in the memory diagram. I need to be able to fit this thing on one slide. So just printing as we visit a node is a lot cleaner in the memory diagram. So let's get into this traversal. We're going to make the first call on the root node, 350. We're going to call traversal 350. That's not null. That's definitely a reference to an object on the heap. So we're going to get to our first recursive call. We're going to call traversal on this node's left node. So node dot left is 200. So we're going to make a recursive call on the node 200. That node is going to do the same thing. It's going to say, well, node's not null, so we're going to make this recursive call on the left. Node dot left. We're going to make a recursive call to null. And that recursive call doesn't do anything. The node's null, the condition's false, doesn't run any code, there's no code outside the conditional, so it just returns. And we're going to see, as we're going through this recursion, we're going to see that this stack is doing a lot of work for us. We're going to see frames pushed and popped all over this stack. We're going to see how much it actually does, see it in full action today. I'd say for the first time, we haven't seen a lot of frames being pushed and popped. So now control gets back to this frame. This is now the top of the stack again. And this stack frame remembers where it was. It remembers that it just made this left recursive call. That call just returned, and it's just going to pick up execution right there and move on to its right recursive call. So 200 dot right, make a recursive call on that node, which again is null. Make the recursive call for null. That does nothing. It just returns. And now this stack frame remembers again. It remembers where it was, that it was waiting for this recursive call to end. That recursive call returned, so now it's going to just pick up right where it left off on the next line of code. Next line of code that needs to be executed, and that's printing to the screen. So it remembers where it was, it picks up where it left off, and then it prints have to the screen, its value. So node for this stack frame is 200 dot value, and we get have. And that stack frame's done. That stack frame reaches the end of its execution. It's popped off the stack, and execution goes back to the next frame that's on the stack. So the next frame that's not crossed out, we go up to this frame, and it continues its execution. This frame, again, knew that it was waiting right here. The arrow knew, these arrows, I just draw the arrows visually. That information is actually stored in the stack frame. In 220, you'll make that more explicit and dive into the details. But each stack frame does remember exactly where it was in its execution. So it remembers that it was waiting for this stack frame to return. So it got control again, so it'll go to the next thing. The next thing to do is making a recursive call on the right, node dot right. We expect a stack frame of 480 as node being added to the stack right here. So we make the recursive call to the right. This node is going to make its recursive call to the left, node dot left. That node is going to make its recursive call to the left, node dot left. And we got all these recursive calls. We have null on the stack, which is just going to return. Gives control back to this stack frame, which just got its return of traversal of node dot left. So it's going to call traversal of node dot right, which again is null. And at this point, we have 4 stack frames on the stack. This is as complex as this example gets, so I want to park it right here for a second and talk through what's going on at this moment, this snapshot of memory. So we have 4 frames on the stack of traversal and another stack frame for the main method itself. And each stack frame remembers where it is in its execution. So we have 4 frames on the stack. These frames, remember, the frames that are crossed out don't exist in memory anymore. So this frame has control right now, and it's about to return and do nothing in return. It's going to give control back to this stack frame, which is sitting right here, waiting for its recursive call to the right to end. So once it gets control back, it's going to print and return. Once it returns, it'll give control back to this frame, which is sitting right here, waiting for its left recursive call to end. Whenever it's done with all of its stuff, it's going to give control back to this stack frame, which is waiting for its right recursive call to end. So when it gets control again, it's going to print its value to the screen and end and give control back to the main method. So we can really see the stack in action here. We can really see the work that it's doing for us in keeping track of all of this bookkeeping, where if you don't want to use recursion, you would have to keep track of all that bookkeeping yourself. The stack is just doing a lot of heavy lifting for us because we're using recursion. Any questions on this? If you understand what's happening right now, you got this down quite well. Which this is a lot of topics, too. This is a lot of topics from previously in the semester. Stack frames, objects references, the heap, recursion, recursive calls, and then, of course, the tree stuff. I don't think the tree stuff itself is too difficult, but the tree stuff is a combination of a lot of things that we've seen over the past 6 weeks. So any questions on any of this? Because if you understand all that, you're quite well caught up with the content, at least with the concepts. My hero. What happens after have is printed when traversal of node.left is called? After have is printed, so have was printed 200 from this stack frame. Then this stack frame ended. This stack frame returned, was removed from memory, and gave control back to this stack frame. This stack frame was waiting for its left recursive call to end. So this stack frame moved on to its next line of code, which was traversal of node.write. So it made another recursive call, which is this one right here, which made a recursive call, which made a recursive call, which returned, which made a recursive call. But this stack frame called traversal on its right child after have was printed, and we went back to traversal.node.left. Hopefully that answered the question. Hopefully I understood that right. All right, so null, this just returns. This stack frame was waiting for its right recursive call. It's going to print to the screen and return. Give control back to this stack frame. It's going to make its right recursive call because it was waiting for its left recursive call. Its right recursive call is null, so it just returns. This node is going to print to the screen. Give control back to the root node, the stack frame. It's going to print to the screen and return. All those stack frames finished up their work, ended, returned, return execution back to the main method, which just ends the program. Any questions on any of that? Hope I understood that question. I think I might have. After have is printed when traversal.left is node.left is called. Okay, if there are no questions, so let's go to my question for you.